The National Electrical Code, specifically Section 250.66, addresses grounding electrodes. Subsection 250.66b focuses on other electrodes, and within that, Part 4 details concrete encased electrodes. A concrete encased electrode is defined as a metal electrode embedded in or encased by concrete that is at least 2.5 centimeters or 1 inch thick and has at least 0.93 square meters or 1 square foot of surface area in contact with the earth. Section 250.66 covers water pipes, outlining requirements for interior and exterior metal water pipes. For an interior metal water pipe, a number 6 American wire gauge or larger copper conductor or equivalent must be used to connect to the metal water pipe. For exterior metallic water pipes, 2 scenarios exist. If the pipe is 5.3 centimeters or 2.1 inches or larger in diameter, a number 6 American wire gauge or larger copper conductor or equivalent is required. If the exterior metallic water pipe is less than 5.3 centimeters or 2.1 inches in diameter, a number 4 American wire gauge or larger copper conductor or equivalent must be used. Given a plastic water line, it cannot serve as a grounding electrode. Therefore, relying on a concrete encased electrode is compliant with NEC 250.66b4. The number 4 conductor to the concrete encased electrode is acceptable in this scenario. However, compliance hinges on the concrete electrode meeting specific requirements. It must have at least 0.93 square meters or 1 square foot of surface area in contact with the earth, and it needs to be encased in concrete that is at least 2.5 centimeters or 1 inch thick. To summarize, the use of a number 4 conductor to connect to a concrete encased electrode is permissible according to the NEC, particularly when a plastic water line prevents the use of the water pipe as a grounding electrode conductor. Ensure that the concrete encased electrode adheres to the size and installation standards to maintain code compliance and ensure effective grounding. Firstly, understand the purpose of grounding. Grounding provides a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. Secondly, recognize the importance of proper conductor sizing. Using the correct size conductor ensures that it can safely carry the fault current without overheating, which could lead to a fire hazard or equipment damage. Thirdly, be aware of the specific requirements for concrete encased electrodes. These electrodes are often used as supplemental grounding electrodes and must meet certain criteria to be effective. Fourthly, remember that the National Electrical Code is a minimum standard. Local jurisdictions may have additional requirements that must be followed. Fifthly, consult with a qualified electrical professional. If you are unsure about any aspect of grounding or electrical work, it is always best to seek the advice of a licensed electrician or engineer. Sixthly, understand the role of the grounding electrode conductor, often abbreviated GEC. The GEC connects the grounding electrode to the grounded conductor, typically the neutral, at the service equipment. Seventhly, recognize that the size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. Eighthly, be familiar with the different types of grounding electrodes that are permitted by the NEC, including metal water pipes, concrete encased electrodes, ground rings, and rod and pipe electrodes. Ninthly, understand the requirements for bonding metal water piping systems. Bonding ensures that all metal parts of the water piping system are at the same electrical potential, reducing the risk of electric shock. Tenthly, be aware of the requirements for equipment grounding. Equipment grounding provides a low impedance path for fault current to return to the source from non-current carrying metal parts of equipment. This is typically accomplished by using equipment grounding conductors, often referred to as EGC. Firstly, grounding systems are crucial for electrical safety, protecting people and equipment from electrical shock and damage caused by fault currents. Secondly, the National Electrical Code, or NEC, provides comprehensive guidelines for designing and installing grounding systems. Compliance with the NEC is essential for ensuring electrical safety and meeting regulatory requirements. Thirdly, grounding electrodes serve as the primary connection to the earth, providing a low impedance path for fault currents to dissipate. Fourthly, concrete encased electrodes, also known as UFA grounds, are an effective type of grounding electrode, especially in new construction where they can be easily incorporated into the building's foundation. Fifthly, when using a concrete encased electrode, it's important to ensure that it meets the minimum requirements specified in the NEC, including the size and depth of the concrete encasement and the type of metal electrode used. Sixthly, the grounding electrode conductor, or GEC, connects the grounding electrode to the service equipment, providing a path for fault currents to flow back to the source. Seventhly, the size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. It's crucial to use the correct size GEC to ensure that it can safely carry the fault current without overheating. Eighthly, metal water pipes can also be used as grounding electrodes, but they must meet certain requirements, including being electrically continuous and having a sufficient amount of metal in contact with the earth. Ninthly, when using a metal water pipe as a grounding electrode, it's important to bond it to the service equipment to ensure that all metal parts of the water piping system are at the same electrical potential. Tenthly, in addition to grounding electrodes, equipment grounding conductors, or EGs, are essential for providing a low impedance path for fault currents to return to the source from non-current carrying metal parts of equipment. Firstly, the NEC specifies different types of grounding electrodes that can be used, each with its own set of requirements. Secondly, the selection of the appropriate grounding electrode depends on various factors, including soil conditions, local codes, and the type of electrical system being installed. Thirdly, when installing grounding electrodes, it's important to follow the manufacturer's instructions and the requirements of the NEC to ensure proper installation and performance. Fourthly, grounding systems should be inspected and tested regularly to ensure that they are functioning properly and providing adequate protection. Fifthly, grounding impedance testing is a common method for evaluating the effectiveness of a grounding system. This test measures the resistance of the grounding path to ensure that it is low enough to safely carry fault currents. Sixthly, ground fault circuit interrupters, or GFCIs, are an important safety device that can help prevent electrical shock by detecting ground faults and interrupting the circuit. Seventhly, GFCIs are required in many locations, including bathrooms, kitchens, and outdoor areas, where there is a high risk of electric shock. Eighthly, surge protective devices, or SPDs, can help protect electronic equipment from damage caused by voltage surges. Ninthly, SPD are typically installed at the service entrance to protect the entire electrical system from surges. Tenthly, it's important to choose SPD that are appropriately rated for the voltage and current levels of the electrical system. Firstly, understanding grounding and bonding is essential for electrical safety and code compliance. Secondly, grounding provides a path for fault current to return to the source, allowing overcurrent protective devices to operate and clear the fault. Thirdly, bonding connects non-current carrying metal parts of equipment and structures to create a low impedance path for fault current. Fourthly, the National Electrical Code, NEC, provides specific requirements for grounding and bonding, which must be followed to ensure electrical safety. Fifthly, a grounding electrode system is a network of interconnected grounding electrodes that provide a connection to the earth. Sixthly, common types of grounding electrodes include metal water pipes, concrete encased electrodes, ground rods, and ground plates. Seventhly, a grounding electrode conductor, GEC, connects the grounding electrode system to the service equipment. Eighthly, the size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. Ninthly, equipment grounding conductors, EGs, provide a path for fault current to return to the source from non-current carrying metal parts of equipment. Tenthly, EGC can be wires, raceways, or other approved metal pathways. Firstly, when working with electrical systems, it's important to follow safe work practices, including wearing appropriate personal protective equipment, PPE, and energizing circuits before working on them. Secondly, lockout-tagout procedures should be followed to prevent accidental re-energization of circuits while they are being worked on. Thirdly, qualified electrical workers should be trained in the proper procedures for grounding and bonding electrical systems. Fourthly, electrical inspections are an important part of ensuring that electrical systems are installed and maintained in accordance with the NEC. Fifthly, electrical permits are often required for electrical work, and it's important to obtain the necessary permits before starting any electrical project. Sixthly, the authority having jurisdiction, OJ, is responsible for enforcing the NEC and other electrical codes. Seventhly, the AHA may be a local building inspector, a state electrical inspector, or another qualified individual. Eighthly, it's important to work with the AHA to ensure that electrical work is done safely and in compliance with all applicable codes. Ninthly, electrical safety is a shared responsibility, and everyone should be aware of the potential hazards of electricity. Tenthly, by following safe work practices and complying with the NEC, we can help prevent electrical accidents and injuries. Grounding and bonding of electrical systems are essential for safety, ensuring that fault currents have a low impedance path back to the source, tripping over current devices, and preventing dangerous voltage buildup. Section 250 of the National Electrical Code, NEC, provides comprehensive requirements for grounding and bonding. The grounding electrode system is a critical component consisting of electrodes such as metal water pipes, concrete encased electrodes, and ground rods, all interconnected to provide a reliable connection to earth. A concrete encased electrode, often referred to as a U for ground, must meet specific criteria, including being encased in at least 2.5 centimeters or 1 inch of concrete with a minimum surface area of 0.93 square meters or 1 square foot in contact with the earth. The grounding electrode conductor GEC connects the grounding electrode system to the service equipment, and its size is determined by NEC Table 250.66 based on the size of the service entrance conductors. Equipment grounding conductors, EGs, provide a path for fault current from non-current carrying metal parts of equipment back to the source, and they can be wires, raceways, or other approved metal pathways. Bonding ensures that all metal parts of an electrical system are at the same electrical potential, minimizing the risk of electric shock. Metal water piping systems must be bonded to the grounding electrode system to maintain electrical continuity. Ground fault circuit interrupters, GFCIs, are crucial safety devices that detect ground faults and interrupt the circuit, preventing electrical shock. Surge protective devices, SPDs, protect electrical equipment from voltage surges caused by lightning or other transient events. Regular inspections and testing of grounding systems are essential to ensure their effectiveness. Ground impedance testing measures the resistance of the grounding path to verify that it is low enough to safely carry fault currents. Always adhere to safe work practices when working with electrical systems, including wearing appropriate personal protective equipment (PPE) and energizing circuits before working on them. Lockout-tagout procedures prevent accidental re-energization of circuits during maintenance. Qualified electrical workers should be trained in proper grounding and bonding techniques. Electrical inspections ensure compliance with the NEC and other applicable codes. Obtain necessary electrical permits before starting any electrical project. The authority having jurisdiction, OJ, enforces the NEC and other electrical codes. Electrical safety is everyone's responsibility, and by following safe practices and adhering to the NEC, we can minimize the risk of electrical accidents. Concrete encased electrodes are specifically addressed in NEC 250.66b. This section allows for the use of a number 4 American wire gauge copper conductor for connection to a concrete encased electrode, provided the electrode meets the requirements of being encased in at least 2.5 centimeters or 1 inch of concrete and having a surface area of at least 0.93 square meters or 1 square foot in direct contact with the earth. In situations where a metal water pipe is not available as a grounding electrode, such as when a plastic water service is used, the concrete encased electrode becomes a primary means of grounding. The NEC mandates that the grounding system must provide a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices. Grounding electrode conductors must be sized appropriately based on the size of the service entrance conductors, as outlined in NEC Table 250.66. Additionally, all metal parts of electrical equipment and systems must be properly bonded to ensure electrical continuity and minimize the risk of electric shock.